is the review of what we talked about last time. Let's go ahead and look at these ideas of motion now in the context of the graph. So on page 129, we're looking at number 4 right here, and we're asked really a series of questions associated with a graph. So first of all, whenever you go to read a graph, let's go ahead and just look through what this graph represents. This graph right here represents the velocity of some object. I believe it explains that we are looking at a particle moving along a horizontal line. So again, maybe just to kind of say, this is not the path of the particle. You can imagine like we have a horizontal line like the one we have right up here that I've drawn. And then we have on this horizontal line a particle that's going to be moving left, and then it's going to be moving right. And again, like this is its initial position right here. And what we're going to be looking at is the velocity of this. So the actual motion of the particle. So that is what this graph is representing. The particle is just going back and forth, and then we're going to be looking at its velocity. So we're asked a series of questions about the motion of this particle, and let's just go ahead and answer these. I believe on the homework they request the answers in actually they use inequalities instead of intervals. So again, just be aware of that, and I'll answer in intervals as we go. So the first thing we're asked is, when does the particle move forward? So if you think about velocity, velocity tells us two things. It's going to tell us the speed and direction. So when the particle is moving forward, we're considering the scenario essentially when the velocity is greater than 0. So if we're thinking about the velocity right here, remember that we're going to be considering essentially the y-axis, or in this case, this is the v-axis. So again, remember the vertical axis represents the velocity here. So we're going to be looking at our vertical axis. So essentially, let's just look at this and then decide, and it's actually already labeled for us, but I just want to make sure we understand the reasoning of these. You can see in the two shaded blue parts, this is where the particle is moving forward. So you can see that the scenario where we have a moving forward is 0, less than or equal to, well, actually it's going to be, I have to always be very careful with the whether it's equal or not. So we'll talk about that as we go. So it's going to be 0 is less than t is less than 3. So that right there captures this first blue box. And what is the other interval when we are moving forward, or the particle is moving forward?
6 is less than t.
Yep, 6 is 7, or 6 is less than t, which is less than 7. So one thing to note about this is we do not need equality here, because if you think about these points right here, this is where it's basically changing direction. So remember, this is the graph of velocity. So at velocity 0, no longer do we have forward movement. So again, that's why we're using non-equal inequalities right here. And then we don't have any information about what is really happening past 7. So we're just considering the domain is from 0 to 7, not equal to, I believe. Yeah, just my notes from here, from looking at the homework, is that the actual information we have, the domain of this function, is going to be 0. Well, here I'll match 0 less than t is less than 7. So again, that's, I believe, what I referenced from my notes when I looked at my math lab earlier. Okay, so when does the particle move backward? So if we think about this in terms of the velocity, this is when the velocity is less than 0. So what interval are we considering when we're considering the particle moving in a backwards direction? Anyone think they know? Grace? It would be right here from 3 to 5. You can see that this is when the velocity is negative, So remember that velocity is telling us speed and direction. So when the velocity is negative, you're moving in it backwards. So you can see, like, if we were to kind of look at this right here is when we had velocity less than 0, and then this is when velocity is greater than 0. It's based off of the direction of the particle. So we have 0, well, actually not 0, it would be 3 is less than t is less than 5. The next question is, when does the particle speed up? Well, if you think about the motion of the particle, it's kind of calling it out right here. So this is where it's speeding up, and this is where it's speeding up. So let's think about, why is that the case? Because if you think about the velocity right here, one more derivative of velocity is the acceleration. So you can think this is where the acceleration is positive, because that is where the graph of the velocity is increasing. But we still want to be very careful when it comes to motion, because when it's talking about speed, it's technically the absolute value. So again, this first part makes sense right here, why it speeds up, because of what I just said about this being the acceleration is positive. So that makes sense. So this is 0 is less than t, which is less than 1. And if we look at this, you can see right here, it says that speed up, even though it's decreasing right here. So we have to be careful, because is this graph right here the graph of the speed? No, it's the graph of the velocity. If we wanted to actually graph the speed, whenever you took the absolute value, what it would look like, this would end up here in the first quadrant, because anything negative would be made positive. So again, you'll have an exercise, I think, later in the notes where it's going to ask us to go ahead and graph the speed. Well, once you have the velocity, you would have to take anything and move it up into the positive quadrant, because the absolute value is not going to have anything down here. So that's also why we have this other scenario where 3 is less than t, which is less than 4. Do we have another interval where the particle is speeding up? Yeah, Alfred, where is it at? You got it, exactly like that, between 6 and 7. So 6 is less than t, which is less than 7. So any questions on the speeding up? Okay, so then we consider the interval where it is slowing down. So, well, here, maybe just maybe put this to words. The answer to this one right here, where it's particle speeds up, you can think about this is where we basically leave the t-axis. So you can see right here, we're leaving the t-axis here and here. We're like going away from it. So where it slows down, this is where we're going to essentially approach the t-axis. So go ahead and take a moment and write the intervals that you think answer the question, when does the particle slow down? While you do that, you take a sip of water. And honestly, the graph kind of gives it away a little bit, but again, just making sure we understand the reasoning. So the first interval was 2 is less than t is less than 3, and the other interval is between 4 and 5. So is everyone okay with the idea of when the particle is speeding up and slowing down? Okay. Now let's consider, when is the acceleration positive? So again, we've actually kind of alluded to this one a little bit here earlier. This is the graph of the velocity. So when we consider the actual acceleration, it's just the same kind of idea we talked about before with the original function. When is it increasing and when is it decreasing? So the acceleration right here is positive. Basically, v is increasing. And as acceleration is negative when v is decreasing. And when acceleration is 0, what can you say about the graph of the velocity? It's going to be constant. It is constant. and maybe one other maybe comment about acceleration being 0, or basically I could word it like this. V is constant, let me say it like this, has a horizontal tangent. That's maybe something to also be aware of, because it's just constant for that brief moment, aka horizontal tangent. So this is also when we would be looking at max or mins. So with that in mind, it's pretty easy to go ahead and answer right here. And so when is it positive? So one thing I made a note when I was going through this problem in the homework is this is 0 is less than or equal to t, which is less than or equal to 1, and 6 is less than t, which is less than 7. So a quick comment about why we have equality right here. Because if we're thinking about this right here, if there was 0 acceleration, oh, I put that in the wrong spot. Hold on, slide that up. So acceleration has to be positive at 0, because if it was not positive, there would be no, basically, no sort of physics to go ahead and push it to have a positive velocity. So that is one thing I noted about the homework when we were doing this one. We have equality at 0 with acceleration, because there needs to be some sort of physical force that's making the velocity come positive. So that's why we're saying that there is an acceleration that is positive at 0, because we're about to speed up. So a little note right there about the acceleration. So it is, where is it negative? So one thing to be careful with this one, because if we look at this, here, let me just see what we want to be careful. Anyone think they know the answer to this one? Anyone want to volunteer it? I want to see what you're thinking. Go on, James. So it's not where the velocity is negative, but it's where it's decreasing. Destiny?
On the interval 2 to 3.
And that's what I was kind of expecting. So we're going to say 2 to 3. And is there another one? Where at? From 3 to 4. Does everyone agree that this is where it is decreasing? But that's one interval. So be careful with this one, because if you're looking at this, it is going to have a negative acceleration all through here. So this might be the answer that will trip you up. That's the right place you're looking. But remember, at t equal to 3, there still is a negative acceleration, because it's one of those things, it's slowing down here, and it's now going to be reversing the directions there. So there's the acceleration. The object stopped for a moment, but the acceleration, the gravity, you can think about gravity. You're going up. So think about it. If I were to toss something safe, my mask, up, it stopped up there for a sec, but did gravity stop? No, gravity was still pushing down. So make sure that you include the 3 in there. So it's 2 is less than t is less than 4. Because think about it in terms of gravity. Gravity didn't stop. The object stopped because it no longer had enough upward velocity to go ahead and push against the gravity, the acceleration. So when is acceleration 0? So there's a couple scenarios. It is right here. It is just keeping a steady state. So it's going to be 1 is less than t is less than 2. There's also going to be the, right here, where it is actually completely stopped. So this is going to be 5 is less than t is less than 6. And there's one more spot where the acceleration, actually, I don't know if that's true. It's saying it's at 4. Would I necessarily say, because that would conflict with the acceleration? speeds up, slow down. I may have to, I have t equal to 4, but something isn't setting right about that. So I may actually, just as I'm teaching this, something doesn't set right about that answer, so I may come back to that in a few minutes. Is that all right? So I have t equal to 4 in my notes, but if we kind of think about this, the acceleration, this is speeding up. Oh, okay, I see why. Because gravity, I was talking about gravity earlier. Gravity doesn't change, but this is a particle that is basically moving. So you can see right here, it is speeding up, and you can see right here, it is slowing down. So all of a sudden, the actual acceleration changed directions. This is good. I had gravity stuck in my head for some reason, and I'm like, gravity doesn't change directions. But in this case, it's talking about the acceleration of the particle. So there is also this instant right here at t equal to 4 that you can see the velocity is speeding up here, and now it's going to slow down. So in order to go ahead and slow down, you need the acceleration, the force pushing you get it in the opposite direction. So t equal to 4 is correct. Just making sure I look at my notes and making sure I've covered everything. You'll find something similar to this in your homework. Okay, any questions so far? Yeah, Destiny.
So I'm kind of a bit confused. So for one of the acceleration negative, it's on the interval from 2 to 4 as it decreases.
Mm-hmm.
So then why is when acceleration is positive, why is the interval 4 to 5 not included?
So I think it's then the connection of these, and that's where my mind got a little funny there for a sec. So just to make sure I understand is like, why do I want to keep t equal to 3 as a negative acceleration? I think is what you're asking about. No? So say your question again.
I understand like graphically, like you see from 2 to 4, like there's like it's decreasing.
Yes.
And that's when the acceleration is negative. But from interval 4 to 5, why is that not considered a positive in the acceleration?
Did I miss it? It looks like I just missed it. Yeah, it should be positive acceleration. Huh? No, that's a good question. I think I just didn't. Particle slows down. So, because it's slowing down, it's because acceleration is essentially pushing against the velocity. So, plus everything needs to be accounted for. So I have 0 to 1, 2 to 4, 5 to 6. So I think I just missed an answer right there. Oh, come back. We're not doing that lesson. So there's one more scenario, and that would be when it's increasing. So, and it would be from 4 is less than t is less than 5, right? That's what you're thinking? Yes.
Yeah,
No, that's good. I think I just missed writing it. That's good. Yep. Any other questions so far? And this is what I meant by questions, because there's a lot to interpret here. So when it comes to acceleration, you can think about it literally as the derivative of velocity. So that's why Destiny brought this up, is because the velocity graph is increasing here, which means when you consider the derivative, it is going to be a positive derivative there. So that's where you would then say the acceleration is positive. Two other questions we have posed down here for us. When does the particle move at its greatest speed? Well, we got to be careful here because, again, speed is the absolute value. So if we were to actually graph the absolute value, I'm going to just put it here temporarily, that was not matching. Let's try that again. Roughly, assuming that I could actually keep it symmetric. That's a little better. This would be what the graph would look like if I was actually graphing the speed. And then you can see this right here is larger than this in terms of the velocity. So again, I'm going to erase that just not to confuse us later. We'll look at an example later. So when does the particle move at its greatest speed? Well, this is at t equal to 4. And again, that's because the speed is the absolute value of velocity. And then the last question, when does the particle stand still for more than 1 instant? So it's actually, you can see that's being called out right here between 5 and 6. That's when the velocity is 0. So this is, if you look at this, this is going to be 5 is less than t is less than 6. So that's kind of where we've been saying, but this is another scenario where you need equality as well. And why is that? The reason you have that is because the moment you hit this right here, it had stopped moving. At time equal to 5, it has stopped moving. It's not like it was just kind of passing through. So this is where it would say, that's why we said more than an instant. If it was just an instant right here, it did have to briefly stop for a minute or moment to turn around. But you can see that's where it stands still for more than an instant. So again, the physics behind the graphs are a little bit tricky. It requires some thought. So here's an example that we worked through together. Does anyone have any questions on any of these problems? So let me give you a few tips on number 5. Whenever it comes to these word problems, you really want to just boil down what you're given and what you're asked. So dynamite blows a heavy rock straight up with a launch velocity of 160 feet, or if we're considering it an imperial, 109 miles per hour. It reaches a height of s equal to 160t minus 16t squared. So again, you can see that we have a couple of things given to us. The first thing we're given right here is that the velocity is equal to 160 feet per second. Again, you may also think about this as s prime, because remember the derivative of velocity, or excuse me, the derivative of position is velocity. So what are we looking for here? How high does the rock go? So if we're thinking about high it goes, we're looking for a type of position. We're looking for s when v is 0. Because if you think about that, at the top of its flight, that rock has a velocity of 0 because it's changing directions. And then remember that whenever a velocity or whenever an object changed directions, it's because the sign changed. So this problem really just boils down to solve s prime equal to 0. The answer to that, again, I'll leave you kind of to work through the details, but the answer, let me reference it from my notes, maybe off to the side I'll put it, is 400 feet. But notice we're looking for a position. So this is really only step 1, because if we solved s prime equal to 0, we get a time. So the second step right here is, so this will give us, like say some, let's just call it t sub 0. And then the solution is the s of t0 is the maximum, or yeah, I'll say maximum height. So this is an outline of how you approach this. To find the maximum height, we're looking for s when v is equal to 0. So if we solve s prime or v equal to 0, that gives us some time. But remember, we don't want the time, we want the height. So we have to then plug that back into the original position function. So that's the first one. Part B is what are the velocity and speed of the rock when it is 156 feet above the ground. So let's think about this. This right here, what is it? Is it a time, a height, a velocity, an acceleration? It's a position, it's a height. Look at the units, feet. So it's not a second. There's no rate of change. So there's not like feet per second or anything like that. It's just, so what we're given here is S is equal to 256 feet. So you solve, setting S equal to 256 feet. What this gives you, this gives us T0 and T1. And what you can see right here is the actual velocity is V of T0. So this is on the way up. This is up. And V of T1 is on the way down. Because it's going to go up. You can see it's going up and it's going back down. So that is a general outline to solve this one. I would encourage you to think through these and, of course, fill out the details. Any questions on that one? I'll let you fill out these. Yes, Savannah.
So would you end up using a quadratic?
You can if you want. I just factored it. I factored it out just using standard methods. You guys want a hint on the last two? Oh, okay. The last two is just take derivatives. Because you're going to need your second derivative, and again at time t, so you don't have to really plug anything in. And when does the rock hit the ground again? If it hits the ground, what is the position? S is equal to 0. So we're given S is equal to 0, so all you have to do is solve S equal to 0. Number 6 asks us to look at this accompanying figure, and again, we're given the graph of the velocity. When does the body reverse direction? When approximately is the body moving at a constant speed? It then asks us to graph the body's speed and then also graph the acceleration. So let me give you a moment to go ahead and try those. All right, let's go ahead and come back together, call out a few ideas, and I want to make a few comments on a couple things and see if that settles well with all of you. All right, so the first question we were posed is, when does the body that is described with the velocity of that body described right here reverse directions? Anyone think they know? Let's see. So you're saying it's changing when it's changing from increasing to decreasing. So you're saying right here? That is not correct. So that's a good idea. But let's just talk about why is t equal to 1 not the answer? This is the velocity. So if you think about it, this is the scenario where the object is speeding up. So if you imagine your car, this is like the light just turned green and you are going up to the next light, and then you see the light turn red, so you got to slow back down. So this is when your foot's on the gas, and then from 1 to 2 is when your foot's on the brake. So that's maybe a way to think about it. So Destiny, I saw your hand as well. What do you say is when the body reverses directions?
I put on the interval from 2 to 7 because velocity is infinite.
So from 2 to 7, so if you think about this, when the body actually, so this is when the car is in reverse. This is not when it reverses direction. So this is very much related to the question we did at the end of last class. Remember, when the velocity changes sign is when it actually reverses direction. Because what you were thinking about is when is it in reverse. So James, what do you think? So 8 to 10 is not quite. This is when it is not 7 to 10. I think. See, I'm glad we're discussing this, right? So 7 to 10. So if we think about it, 7 to 10 is, so this part right here. Let me go ahead and maybe just kind of call out this part right here. This part from, let's say, just the one where it's kind of a little bit different. It's on the gas pushing down. So this is again, there's some force that's pushing it through. So again, we're just looking, where does the graph change signs? Let's go to Griffin.
At 2 and at 7.
2 and 7. So the answer to A is the point specifically 2 and specifically at 7. So t equal to 2 and t equal to 7. So this is when your car was stopped just enough so you don't like drop your engine or something, but it's when you're shifting from drive to reverse. There and there. Very good. Any other questions on A? And then for those of you who post the intervals, and I think we were thinking a lot about intervals, so that question was just slightly different. Any other questions there? Say, yeah.
I was just gonna make sure, and you covered it.
No, ask away.
Make sure that, like, if that was, like, if that question was on, like, homework or a test, is that how you want to write it?
Don't stress too much about form. Basically 2 and 7, or maybe if it's multiple choice. I haven't written the exam for this semester yet, so ask me on review day and I'll be able to give more insight. All right, the other question, B, when approximately is the body moving at a constant speed? Anyone think they know right here? James, let's try again.
So the constant is at the bottom, right? 3 can be, 3 is
Okay,
less than t, and t is less than 7.
less than, too far.
Boy, 6.
6, because again, 7, you start slowing back down. So this is the car speeding up in reverse. This is basically where you put on cruise control in reverse. I don't know if cruise control even works in reverse. Never tried it. Not that great of a driver. But one thing that we want to we look at, this is the moment that it was put into cruise control, assuming your cruise control works in reverse. So you do include equality there. Because 6. I was just looking at James's cool shades right there. It's like, here you go. What's up, Emma?
I'm sorry, can you clarify what we're supposed to use, like, equal to one more time?
Oh, a lot of this does come down to just really thinking about the actual physics going on right here, the actual motion. So in this case, we're going to use equality is because if you think about this moment right here, there's no more acceleration. If there was some acceleration right here, you would have actually more motion going downwards right here. So the principle right here is we're using equality is because at this moment, there is 0 acceleration, so it is now moving at a constant speed. It does take some thought, which is also kind of back up here. A lot of you kind of are thinking about what's going on with the derivative or the acceleration. So you can see the other scenario up here, we used equality when t is equal to 0 because we needed to have some sort of force getting ready to increase the velocity, and that force being the acceleration. Okay, any questions on A or B? All right. So C is not too bad. So what you're going to do is let me go ahead and scale this. So right here is 3. So you can see the first part of the graph is going to match. So I go from, so I'm just kind of taking that part right there and putting that up into just translating that down to the new graph. But the thing we have to be careful about is this part right here where the negative velocity. So it took us from 0 to 3 to get there, and then you can see from, 1, 2, 3, 4, 5, 6. Yep, good. That is where it was constant, and then from 6 to 7, it got back down here. And then from 6 to 8, it went back to 3, and then from 8 to 10, it went right down there. So this is the answer. I don't know, to me it looks like half the face of Batman or something with the little wings. Okay, maybe that's a stretch, but we'll just speed right through that one. Any questions on that one? How many got that? A couple of you, very good. So I kind of alluded to that one a little bit earlier. Okay, and then the graph of acceleration. So if we think about this, let's think about this based off of what we already know about functions. I'm gonna go ahead and clean up the graph a little bit just up here. This piece right here is what type of function? Linear. So the derivative of a linear function is what type of function? Constant. And constant functions graph look like horizontal lines. So to figure out the derivative here, consider the slope. We did 3 over 1, or 3 is the slope of that first little orange part. So from 0 to 1 on the graph of the acceleration, we have to have we have to be at 3. So that's going to be right here to here. So I believe with the accelerator, so let's again think about equality here. So I put open dots, and the question is that right or wrong? What we want to think about it. Since nothing was described over here at 0, remember we said earlier acceleration it was included with equality. So I'm going to close this dot off at 0 because again there needed to be some sort of acceleration to get that forward movement. But do I want an open or closed dot here? If you think it should be open, give me thumbs up. If you think it's closed, give me a thumbs down. Right, so I see thumbs up or no answers. And for those who said thumbs up, that is correct. The reason it is an open dot is because, remember, if we have a sharp turn, the derivative does not exist at sharp turns. Destiny, did you have a thought or a question? No, just kind of thinking. Awesome, being engaged. Awesome. So this is an open dot. The next one interval right here, let's see, that is from 1 to 3. What is the slope of this one? Again, you can always just it's going to be -6 over 2. So you can see that the slope here, the m, is -3. So, well, this doesn't work out very well because the graph should actually exist down here. So we would have this right there as the graph of the acceleration. And again, continue open dots. Does everyone see how I'm getting the graph of the acceleration? I'm just considering the slope of each piece. Then we have this piece right here from, let's see, that would be from 3 to 6. What is the slope of that part right there? If it's horizontal, the slope is 0. So it's going to be from 0 to the slope is 0 from 3 to 6. 3, 4, 5, 6, just keeping my scale correct. So you can see that's where the graph of the acceleration is at 0, because what this represents right here is the vertical axis is the slope of the original function here being velocity. So just one more derivative. So go ahead and let's look at these last two. So this one is going to be, let's see, how much do we rise? It looks like we rise 6, run 2. So again, the slope is 3 here. So we're back up here. And that goes from 0 to 8. And then the last one, let's find one more color. It looks like blue. We go down 2, run 2, so the slope is going to be 1. So right there, this step function is going to be the graph of the acceleration. Any questions on that one?